Yes, good morning, students. We were discussing about BPSK generation and detection, right, in the previous class. And yeah, so are we able to see the slide? Hello? Hello, am I audible?
Yes, sir.
Yeah. So this was the block diagram of BPSK transmitter and coherent binary phase shift keying receiver. Okay. So what I said as far as transmitter is concerned, so we were having this binary data sequence, right? That will be first passed through the polar NRZ encoder. Okay. So once I say polar NRZ encoder, I will be representing binary data or binary symbol 0 by a negative pulse and binary 1 by a positive pulse, right? And I am considering the amplitude of that pulse will be uh, plus root EB for symbol 1 and minus root EB for symbol 0, right? So that will be given as one input to the product modulator, and another input to the product modulator is the basis function, which we consider as carrier. Okay, so which we denote as pi 1 of t, which is equal to root of 2 by tp cosine of 2 pi of ct. So the multiplication of these two leads to the BPSK signal, so which we denote as S of t. And I said, how do we express mathematically this S of t, right? So which is equal to square root of, that is we say what is how do we represent for symbol 1 and symbol 0, right? For symbol 1 we call that as S1 of t, which is equal to square root of 2 EB by TB cosine of 2 pi of CT. And for symbol 0, we say it is S2 of t, which is equal to square root of 2 EB by TB cosine of 2 pi of CT plus pi, right? So there is a phase shift of 180 degree. So which is equal to what I can write, minus square root of 2 EB by TB cosine of 2 pi of CT, right? So looking at that, okay, so that is the binary PSK signal, which will be transmitted over the channel, and we denote the received signal at the receiver side as x of t. So which is equal to what? S of t plus the noise will be there. So we consider that noise as the additive white Gaussian noise, and that received signal will be given to the correlator. So we all know what correlator consists of, right? So correlator will have a multiplier followed by an integrator, and here whatever the basis function what we use at the transmitter side, the same basis function will be used at the receiver side also. Means what I mean to say, it is a carrier, right? So whatever the carrier is used at the transmitter side, the same carrier which is synchronized with phase and as well as frequency will be used at the receiver side. So that is why it is called coherent. Okay, why it is called coherent binary PSK receiver is that whatever the carrier signal we use at the receiver side for recovering the transmitted signal, so the same carrier will be used at the transmitter side, right? Then output of this correlator is in what? Observation vector x, right? So this x1, what we get will be compared with the threshold value. So how do we decide this threshold value? I have told with respect to the signal space diagram, right? So the purpose of this decision device is to take a decision based on the value of the received signal vector when it is compared to the threshold value, right? So it will be taking a decision in favor of symbol 1 when the value of this x1 is greater than 0, because with respect to the signal space diagram, I said the symbol 1 will be lying in the region Z1. So we take that is the decision boundary is exactly at the origin, right, which is starts from 0. And I said this zeros and ones occurs with equal probability, right? And so when the value of x1 is less than 0, so the decision will be taken in favor of symbol 0. So this is what the working of BPSK transmitter and receiver. So let us try to understand and try to derive the expression for what is the probability of bit error rate. See, while taking a decision, no, because I will come to that. I will come to that. What is that? I think just to show, sorry. Yeah, this is what the signal space diagram I said. Just I wanted to recap. All of you just have a look, right? So this is what the signal constellation diagram or signal space diagram for the BPSK said, right? So it has one dimensional, means I have only one basis function. So I said this is message point 1. What I mean to say it is S11, what I can say. So which is equal to square root of EB. And this one is S21, right? Which is equal to minus root EB, right? So this is my decision boundary. Above that will be taken in favor of symbol 1, and means if the value of x1 lies in this region, I can take the decision device will be taking a decision in favor of symbol 1. And if the value of x1 lies below the 0 value, then the decision will be taken in favor of symbol 0. That is the message point 2. Okay. So with this recap, as I was telling that, let us try to understand and derive the expression for probability of average probability of bit error rate, right? So with respect to this diagram only, let me say one more thing. So I said the decision device will be taking a decision based on the value of x1 where it lies, right? Let us assume that there are two possibilities of getting error. So is it possible to say what are those two possibilities of error? Yes, my dear students, are you understanding what I'm saying? So with respect to this decision, what I said, if the value of x1, right, is greater than 0, means this is a threshold value, right? This is my decision boundary. If it is greater than 0, the decision device will be taking a decision in favor of symbol 1, right? If the value of x1 is less than 0, then the decision device will be taking a decision in favor of symbol 0. If the value of x1 exactly lies on this line, exactly lies on the decision boundary, then it will be a random decision. That is, by tossing a coin, it will be taking a decision. Okay, that is what we say. And what I am asking here is, what are the possibilities of making a wrong decision? Is it possible to think and say?
1 by 2. 0.5.
I am not able to. Pardon? It is
0.5, sir.
pardon. Yeah. Hello.
0.5.
Yes, I'm unable to hear your voice. Is it possible to talk loudly a little bit?
Sir, the
Maureen?
probability is 0.5.
No, I'm not asking about the probability, whether it is 0.5 or that. I am asking about, see, the received signal, no? It will be having a noise also, right? Transmitted signal along with the noise, right? So if the noise is more, right, let us assume that the symbol 1 is transmitted. Okay, symbol 1 is transmitted, and the level of noise is such that the value of that x1 goes below this threshold value. Okay, then the decision device will be taking a decision in favor of symbol 0, right? But actually the transmitted symbol was 1. That is one case. Hope you're understanding what I'm saying.
Yes, sir.
Let us assume that the transmitted symbol is 1. When it is transmitted over the channel, the noise will be getting added, right? So with the addition of that noise, at the receiver side, the value of x1 may be less than 0. Okay. Right. In that case, the decision device will be taking a decision in favor of symbol 0. Okay. Actually, the decision device has to take a decision in favor of symbol 1 because the transmitted symbol is 1. That is one possibility is there. Another possibility is what? When symbol 0 is transmitted, right, the received signal is such that the value of that will be greater than 0. Right? Now the decision device will be taking a decision in favor of symbol 1. But actually the symbol 0 is transmitted. I think these are the two possibilities of going or getting error, right? When 1 is transmitted, if the decision device is taking a decision in favor of symbol 0, that is one error, what we say. And second one is what? When symbol 0 is transmitted, and if the decision device takes a decision in favor of symbol 1, then that is another error, right? Hope got my point, my dear students.
Yes, sir.
Thank you. Okay, let us try to understand how do we compute that the average probability of bit error by assuming the zeros and ones, that is our binary data, occurs with the equal probability. Okay, they are equal probability. Okay, so I will skip these two slides. I think I will, if necessary, I will come back. Okay, so this is all about just saying about what the coherent receiver is having. Okay, so basically what we say, the coherent binary receiver has two main components. One is the correlator and second one is the decision device. Okay, first one is the what? Correlator, and second one is the decision device. Fine. So I said what the correlator will do, right? So the correlator will correlates the received signal with the basis function on bit by bit basis, right? So what decision device will do? It will compare the output of the correlator against the threshold value, and here I said the threshold value is 0, right? And it will and as well as we have assumed that the binary symbols 1 and 0 are equiprobable, right? So if the value of x1 exceeds the threshold value, then the decision will be made in favor of symbol 1. Otherwise, the decision will be taken in favor of symbol 0, right? And as I said about this point, that is equality of the correlator with the 0 threshold is decided by the toss of a fair coin. So that is random in nature. Okay, fine. So even I told this point also. What are the possibilities of taking a wrong decision, right? So this all I hope you are aware. How do we represent the message point 1 with what value, right? That is plus square root of EB, and message point 2, that is symbol 0 by minus square root of EB, right? So what I wanted to say here is, already I told about that. What is that? So the I said about the two regions, right? Z1 and Z2, how the decision will be made, right? So the possible erroneous decisions, what I said is first one is, means the first kind of error is what? When signal S2 of t, S2 of t means the symbol 0, right, is transmitted, but the noise is such that the received signal point falls inside the region Z1. So the receiver will be deciding in favor of signal S1 of t. Okay, so this is with respect to one error. Okay, another error is what I said, when S1 of t is transmitted, but the noise is such that the received signal point falls inside the region Z2. So the receiver will be taking a decision in favor of signal S2 of t. Right. So let us try to understand how do we compute this error. Okay. Yeah. Yes, to calculate the probability of making an error of the first kind, that is S2 of t is transmitted, right? The receiver noise is such that the signal will be lying in the region Z1 and decision will be taken in favor of S1 of t, right? So what is that error? So how do we do that, right? So to calculate the probability of making an error of the first kind, that is the decision region associated with the symbol 1, or what I can say the signal S1 of t, how do I describe that? So the value of x1, right, will be less than infinity but greater than 0, right? So that is with respect to region Z1, right? So here the observation vector, that is x1, we know how to relate that, right? So it is just output of the correlator, what is written, right? X1 is equal to integral 0 to TB x of t pi 1 of t into dt. Yes? Hope you are able to understand what I am saying. So just I am saying this expression is what? It is the output of the correlator. Okay. Then how do I define the conditional probability density function of the random variable x1? Right. Given that the symbol 0 was transmitted. Right. So already we are aware. Right. What is the, how do we define that conditional probability density function? Right. So what is that? The conditional probability density function of the random variable x1 given that symbol 0 was transmitted. Okay, symbol 0 is transmitted. So if x1 of x1 is a condition, right? 0 is transmitted. So we write 1 by root of pi n naught e power minus 1 by n naught of x1 minus s21 whole square. Right? I hope you have remembered the general expression. Here the value is substituted. Okay, still it is written in general only, but s21 is what? It is the mean, right? Mean of this random variable. So that is why the previous classes lectures are important. Okay, so if you are aware of that expression, the conditional probability density function, easily you will be able to understand this equation. Is any questions to ask with respect to this? Yes, my dear students, if you don't have questions, I will go to the next slide. I said what is this equation is, right? It is the conditional probability density function of the random variable x1 given that the symbol 0, that is signal s2 of t, was transmitted. Okay. Yeah. Yes. Yes. Any questions with respect to previous slide? Hello. Yes, my dear students, do you have any questions?
No, sir.
Okay, thank you. So if that is done fine, then let me go to the next slide. I think I don't know what you people all will do. Are you noting the equations or just listening? Because with respect to writing, I will be a little bit slow. But when I go with the slide, I think I feel fast. If I am fast, please hold me. Okay. At least you should be able to grasp the concept, right? I said, what is the output of the correlator? You all know very well how to write that, right? X of t is the input, pi 1 of t is the basis function, multiplication, then integration over the interval, small interval. That is what x1 value. And I said this is the expression for conditional probability density function of the random variable x1 given that the symbol 0 was transmitted. Right? So now I know what is the value of S21. Right? S21 is what? It is minus root EB. Right? I think. Yes, are you aware or not how to find S21 and S11? You know, no? Yes, people should respond. You know how to find S11 and S21 because I know what is S1 of t and what is S2 of t. How do I express S1 of t? Yes, I want some response. What is the expression for S1 of t? Yes, quickly, some people should respond. S1 of t. Hello. How do I express the signal S1 of t in terms of orthonormal basis functions? I'm asking. S1 of t. Yes, quickly. Yes, why no response? Already people have forgotten or what? See, every time I will not be able to bring back and say what is it. Yes.
S11 into 5 of
Yeah. See, here it is in this slide is shown now. See S1 of t. So the value of root EB is nothing but S11. Okay. So S1 of t is equal to S11 pi 1 of t. So S11 value is plus root EB, I can say. Similarly, S2 of t is equal to S21 pi 1 of t. So the value of S21 is minus root of EB. So you know how to find S11 and S21. I need not again stress upon that, but I expect you to respond. Okay. That is why I say to be with me. Fine. So with that equation, so what I am hope are able to understand the previous this conditional probability density function equation, and just I am substituting the value of S21 in this equation, in the previous equation. Okay. So what I did here, this is the conditional probability density function, right, of the random variable x1 when 0 was transmitted, right? So I just substitute the value of S21 as minus root EB. So that is why I have written here x1 plus root of EB. Okay, so minus of minus root EB becomes plus root EB, that whole square. Fine. So then the conditional probability of the receiver deciding in favor of symbol 1. Okay, the conditional probability of the receiver deciding in favor of symbol 1, given that the symbol 0 was transmitted, means this one, right, is what? This one. That is, we denote that as P10. So P10 is the what? Is the conditional probability of the receiver deciding in favor of symbol 1. Right? When symbol 0 was transmitted. So which is equal to what? 1 by root of pi in n naught. Right? So integral 0 to infinity e power this just value minus 1 by n naught of x1 plus root eb whole square into dx1. Okay. Yes, you understood this question, this equation, how I got this one? So I know this equation, right? So to find the conditional probability of the receiver deciding in favor of symbol 1, given that symbol 0 was transmitted. So what I used to write? So integral of this one, right? Integral of this one, that is why I have taken. So 1 by root of pi n naught, I have taken it outside the integral. So the rest of the things are there inside the integral into dx1. Okay. So here by substituting and taking what the variable adjustment. Okay. So I can take z is equal to root of 2 by n naught of x1 plus root eb. Okay. So if I take z is equal to root of 2 by n naught of x1 plus root eb, then what I can write? Is it possible to simplify and say I am letting z is equal to that? Okay. Letting z is equal to root of 2 by n naught of x1 plus root eb. Yes, is it possible to say? Just we have to work out because what we can say. So if I let z is equal to root of 2 by n naught into x1 plus root eb, then you have to change the variable of integration, right? From what? X1 to z. Okay, you have to change the variable of integration from x1 to z. Then by doing that, and you know, are you aware of the q function? Yes, I'm asking you people only. Are you aware of what is q function? Yes, my dear students. Are you aware of complementary error function and error function ERF and ERFC? Yes, no response only. Yes, I'm asking, are you aware of what is error function, what is complementary error function? So if you know those things, then you'll be able to relate with the Q function. No idea. Fine. If you're not aware, just have a look about the probability part of your linear algebra. you will be able to understand that. So now, just what I said, I am letting z is equal to this, okay, square root of 2 by n naught of x1 plus root EB. And what I said, I will be changing the variable of integration from x1 to z in this expression. Okay, so by doing so, I can write the expression in a very compact manner. And what I said, so which is equal to what? P10, okay, P10, which is equal to 1 by root of 2 pi. So limits have been changed, right? Initially it was from 0 to infinity. Now, since I'm letting z is equal to what I said, root of 2 by n naught of x1 plus root EB. So with that, the limits have been changed from root of 2 EB by n naught to infinity. Okay, and it is in compact form. So e power minus z square by 2 into dz derivative. So what is z? I said z is equal to root of 2 by n naught of x1 plus root EB. Okay, so just to write in compact form so that it will be means I will be able to say means e power uh, means in this form. If it is there in this form, I can say it is a q function. Okay, entire thing can be written as in the form of q. So that is why. So P10, what is this P10? I said it is the conditional probability of the receiver deciding in favor of symbol 1 when symbol 0 was transmitted, right? So this is what I express it in the standard q function. I can write P10 is equal to q of root of 2 EB by n naught. Okay, so this is how we write what is the conditional probability of the receiver deciding in favor of symbol 1 when symbol 0 is transmitted. Okay, as I said, these zeros and ones are occurring with equal probability. Then I can equate, no, P10 is equal to P01. Okay, P10 is equal to P01. So by averaging, okay, by taking average of that P10 plus P01 by 2, right? So the average probability of error, which is denoted as P suffix E, will be expressed in terms of q function only. So which is equal to root of 2 EB by n naught. So in between steps, maybe 1 or 2 steps are there with respect to that integration, changing limits. Just try to understand that. If you are not able to get that one, I can help you. Okay, but I want response from your end, because if I keep writing every step, even then I am not getting response, then what is the motivation for me? Okay, so what I said is means with respect to that error, what I said, the symbol 1 and 0 uh, will be occurring with equal probability now. So by taking the average, by averaging the conditional error probabilities, that is P10 and P01, and we can find the average probability of symbol error. Okay, this average probability of symbol error, it is also known as bit error rate, BER. So it is a very, very important parameter for estimating or for finding the performance of any given modulation technique, what I can say. Okay, so based on this value of BER, we will be able to say how good that particular modulation technique is. Okay, so that is why I try to be attentive and try to understand what it is. Fine. So I said the average probability of symbol error, or I can say it is a bit error rate. Okay, so for binary phase shift keying using coherent detection. Okay, even non-coherent is also there. That is why we are stressing upon coherent detection. Okay, this is for coherent detection. For non-coherent detection, it will be different. Okay, so the bit error rate for binary phase shift keying using coherent detection, and assuming the symbols are equiprobable, so I can say what is the average probability of symbol error. So which is equal to q of root of 2 EB by n naught. Okay, so looking at this expression, what we can conclude or summarize is, means what I said, this EB is nothing but what is the transmitted signal energy, right, per bit. EB is the transmitted signal energy per bit, and Actually, it is EB by N naught by 2 we can write, right? N naught by 2 is the what? Is the power spectral density of the additive noise, right? So that 2 will be taken in the numerator. I hope you all understand that. It is simple to understand also, right? It is nothing but what? EB by N naught by 2. It can be written as root of 2 EB by N naught, right? Means what I wanted to say here is, uh, see, with respect to the message points, right? That is either symbol 1 or symbol 0. What happens here? The average probability of symbol error is directly proportional to what? The signal energy, right? Transmitted signal energy. So if the value of EB is large, means if I increase the signal energy, okay, if I increase the signal energy, then these message points, which are what we are shown in the signal space diagram, will be again moving farther away from the origin. Okay, so when they move farther away, then the possibility of error will be less, right? So the average probability of error is going to be reduced. Okay, so that is what the meaning of this equation is. Okay, hope you are able to understand what I am saying. See, the average probability of symbol error is directly proportional to what? The signal energy. That is the transmitted signal energy. Okay. So if the transmitted signal energy is increasing, then what I said, the message points which have been shown in the signal space diagram will be moving further away from the means they are moving further away from the origin, right? Means it is, we are increasing the distance between the message points, right? So with that, the possibility of wrong decisions is going to reduce. Okay, so the average probability of error will be reduced if the transmitted signal energy is increased. Okay, so I hope you are able to understand what I am saying. Yes,
Yes, sir.
except maybe with respect to this Q function, I have not done in between steps what I frankly saying, because I said by letting the variable z is equal to this, then you will be able to say what is x1, right? What you are supposed to substitute dx1 as, right? So dz is equal to what you will just find out. Just it is a matter of 2 minutes. If you think you will be able to do that, and you will be able to arrive to this expression, and this is how we define the q function. So that is why entire thing is replaced by the q function. Okay. Yeah. So this is all about the probability of error. Okay. So very few steps are there, and it is an compulsorily they will ask one question on deriving this probability of error, average probability of error, either for BPSK, QPSK, whatever the modulation techniques are there now, around 4 to 5 you are studying. So you have to understand this as basic. Fine. So then let me go to the power spectral density of this BPSK signal, right? So how do we uh, see the power spectra of this binary PSK signal, right? So with respect to understanding the power spectra of binary PSK signal, what I wanted to say is with respect to the log diagram of this BPSK generation, so it is a product modulator, right? So input is your binary data, which is encoded by polar NRZ form, and another is a carrier, right? So when you multiply that, I said we will be getting BPSK signal. And we know that for symbol 1, it is a cosine function. For symbol 0, it is minus cos function, right? So here there is a phase reversal, right? Phase reversal means I hope you all might have remembered we got that in even in DSBSC also, right? In with respect to analog modulation, that is DSBSC, right? That is double sideband suppressor carrier modulation. Whenever the signal crosses zero reference line, there was a phase reversal of 180 degree, right? So it is similar to that, similar kind of that. That is why I came back to this slide to just to say that. Fine. Now what I wanted to say is how do we visualize the power spectrum of this BPSK signal? right? So to understand that, uh, let me represent the pulse shaping function, what I denote that as g of t. Okay, so g of t will be representing was what? Pulse shaping function. That is what I said now, input binary data, zeros and ones will be passed through polar NRZ encoder, right? So that polar NRZ encoder, the shape of that pulse I can represent mathematically like this. That is root of 2 EV by TB over the interval 0 to TB. Otherwise, it will be 0. So why I am taking this? So depending, so this is my G of T. Okay. Yes, hope able to get the idea. I represent the polar NRZ waveform, which I denote as what? G of T is what? Root of 2 EB by TB over the interval 0 to TB. Okay. And it will be 0 elsewhere. Means depending upon whether it is symbol 1 or symbol 0. Okay, if it is symbol 1, I represent this by plus g of t. If it is symbol 0, I represent this by minus g of t. Means for symbol 1, it will be plus root of 2 EB by TB. For symbol 0, it will be minus root of 2 EB by TB, what I wanted to say. So with respect to that, so that one only is told here. Okay, so depending upon whether the transmitter input is binary symbol 1 or 0, so the corresponding transmitter output will be what? Either it will be plus g of t or minus g of t. Okay, so it is assumed that the incoming binary sequence is random, right? Means incoming binary sequence is random with symbols 1 and 0 with equally likely, being equally likely, and the symbols transmitted during the different time slots being statistically independent. So this sentence is very very important to apply your knowledge, whatever you have we have derived. What are the things, right? About we verified that the output of the correlators are statistically independent, right? So those things are helping here to understand. Okay, so what is assumption is made? The incoming binary sequence is random with symbols 1 and 0 being equally likely, and the symbols transmitted during the different time slots are what? Statistically independent. So with that, I think you may be having some idea about how to draw the energy spectral density and as well as the power spectral density of the given binary random wave. I think even I remember I have shown you people what will be the autocorrelation function of the binary random wave. Okay, so it will be of a triangular type. Okay, for the random binary wave, the autocorrelation function will be of triangular type. So how to find that energy and power spectra is here what I have shown with respect to the power spectra. What I have shown is a single sided, and it will be, since it is symmetric, it is shown only one sided. You can write with the other side also for negative frequencies. Okay, so you consider this one only. See, this is for binary PSK, whatever I am moving the cursor now. So this is the power spectra of the BPSK signal. Okay, and this is how we write the, means after taking Fourier transform of that signal, right? We will be getting this one, that is 2EB sine square of pi TBF divided by pi TBF whole square. So it is nothing but sinc square. So 2EB into sinc square of TB into F. Okay, whatever that G of T is there, which is multiplied, I said it is root of 2EB by TB, right? So which is means S of t. I think you can think in terms of S of t. So S of t is what? Root of 2 EB by TB cosine of 2 pi FCT, right? So you take the Fourier transform of that. Okay, so that will be your this one. So I think I am skipping some of the derivations in between. So by this time, I hope we'll be able to understand that. Means it takes time. Okay, to derive this only, I may need to spend half an hour time. So that is why At this point of time, just I am saying what is the expression for the power spectral density of that signal and how does it looks graphically. Okay. Yes, is that fine?
Yes,
So
sir.
this is the power spectra of our binary PSK signal, and I said which is symmetric about the vertical axis, right? And this SB of F, no, this SB of F will be passing through 0 at multiples of the bit rate. That is F is equal to. So this is what this is plus or minus 1 by TB I can say. Then this is plus or minus 2 by TB and so on. Okay. Hope you are able to visualize a sync function, right? You can visualize a sync function with here only one sided I said is shown. With respect to this, you can visualize the other side also, and it will be passing through 0 crossing set plus or minus 1 by TB plus or minus 2 by TB and so on. Okay. Yes, sometimes they ask this also power spectra of so and so. I think we should be able to reproduce this. Fine. So this is all about BPSK, what I wanted to say. Yes, if you have any questions, you can ask. Otherwise, I will proceed further to the next one. Yes, I am saying from my side, of course, in between some of the steps I have not shown. So I think you try it. If you're not getting, I can help you. Okay. So I assume if you're not asking any questions, let me take up the next topic. So that is the quadrature phase shift keying, QPSK. Yes, if you have any questions, you can ask. Please be open because these topics are important, and you are conducting lab also about all these modulation techniques, right? And you are going to verify that average probability of symbol error also. Okay, that is you are going to draw P versus EB by N naught graphs. Okay, you can even refer my videos which I have uploaded in the last year. Fine. Yes, if you do not have any questions, let me proceed further. Yeah, the next one is the quadrature phase shift keying. It is also known as quadriphase shift keying. Okay. See, what we need to understand in a communication system is that is reliable performance. Okay. So, which will be exemplified by the very low probability of error. Okay. When I say the performance of a digital communication system is reliable, means it should have a very low probability of error. Means if I am able to hear 100% information correctly, then I can say the system performance is good. Even at what places? Even when the signal strength is low. Okay, even at when the signal strength is low. That is one thing. Another important goal is the efficient utilization of the channel bandwidth. Okay, so this is very important. See, you all know how much valuable the spectrum is, right? In that sense, the efficient utilization of the channel bandwidth is an important goal. What we need to look into the design of digital communication system. So keeping that in mind, so how do we utilize the available bandwidth as efficiently as possible? Okay, here the efficient utilization means what? If I am able to transmit more number of bits with the available bandwidth, then I can say, yes, I am able to achieve more data rate, right? Means if I use BPSK modulation, I will be able to transmit only 1 bit per second. Okay, 1 bit per second. Let me see how this QPSK is able to transmit 2 bits per second. Okay, 2 bits per second. That is why it is called a bandwidth conservation modulation scheme. Okay. Yes, my dear students, are you okay?
Yes, sir.
Yes, sir.
Okay. So just I think it is. Let me have 1 or 2 minutes of discussion. I think at least Anand, Skanda, Naureen, and all responding. Kuber also. And what about other people? You know, yes. Let me ask some questions for some people. Let me try to understand their understanding. Yes, Chandan. Chandan.
Yes, sir.
Yeah, can you just say how do we convey the binary information by using BPSK modulation? Skanda, not Skanda, sorry, Chandan. Chandan, have you understood my question? Hello, Chandan. Yes, unmute and talk, no? Chandan? Yes, Chandan, what happened? Chandan?
Yes, sir.
Yeah, what, man? You are taking so much of time to unmute and say yes, sir. Have you understood my question?
No, sir.
No. So you have not understood my question only. I asked you, how do we convey the binary information by using BPSK modulation? I said. Yes, you should tell now whether you have understood my question or not. If you have understood, is it possible to answer my question or shall I go to the next candidate?
I don't
Something
know
should
the
be
answer,
there.
sir.
You have you understood the question at least,
I understood the question, sir, but I don't know the answer.
but you don't know the answer. Okay, at least good. What about Bharti? Bharti. Oh, it is a very big challenge for me, making you people to unmute and talking to you people. Yes, Bharti. So that fellow is not responding only. Yes, what about Girish? Girish.
Sir,
Yeah. Have understood my question, man.
yes, sir.
Can you answer?
Sir, binary data sequence.
Uh, yeah, I have asked how do we convey the binary information by using BPSK modulation, I said.
Yes, sir.
Means the information will be carried where? By which signal and how does it conveys the, oh, it is binary 0, oh, it is binary 1, like that.
Uh, S1 of t and
That is fine, man. S1 of t, S2 of t is fine.
yes, sir.
I am asking you which signal, okay, will be carrying that information, binary information, with respect to what parameter? Whether it will be there in amplitude or whether it will be there in frequency or whether it will be there in the phase of the carrier signal, I'm asking, man. Not got my point. See, I said modulation means what? Either we are varying amplitude or frequency or phase of the carrier signal in accordance with the message signal, right? So here, in case of binary phase shift keying, which parameter of the carrier signal is varied in accordance with the message signal, I'm asking. Okay, what about Karunya? Yes, Karunya. Hello, Karunya. No. Leah. Yeah, please respond. Now I've asked the question. Do you have answer? Yes, Leah. Not able to
Phase, sir.
unmute. Yes, Leah. Leah, I'm asking Leah. Leah also not. What about Manasa, Arya, Manasa?
Yes,
Yes,
sir.
Manasa, Arya. Yeah. Can you answer, ma?
Sir, phase is varied, sir.
Very good. Right. I said in case of
In
binary phase
accordance
shift
with carrier
keying,
weight.
no, in accordance with the message signal. Okay.
Okay, sir.
So yeah, means the information is carried in the phase of the carrier signal. Okay. That is what I wanted to say. The information, either whether it is symbol 0 or symbol 1, is carried in the phase of the carrier signal, right? For symbol 1, it will be a cosine signal. I said for symbol 0, it will be minus cosine. Means 0 degree and 180 degree phase shift, right? So with the change in the phase of the carrier, means by looking at the phase of the carrier, I will be able to understand whether 0 is transmitted or 1 is transmitted. That is why it is called binary phase shift key. Okay. Okay, fine. So just let me continue for another 5 minutes with respect to this QPSK. Okay, I was telling in BPSK we are able to one minute. Yes, yeah, I was saying na in. Yes, am I audible? Hello?
Yes, sir.
Yeah. So in case of BPSK, I'm able to transmit only 1 bit per second, right? So I said the QPSK is known as a bandwidth conservation scheme, and let us see how many more number of bits I can transmit in case of QPSK. As already said, I will be able to transmit here 2 bits per second. So let us try to understand how we are able to transmit. Means as far as bandwidth is concerned, same. Whatever the bandwidth available for BPSK, the same amount of bandwidth is also available for QPSK. But by using QPSK modulation, I am able to transmit 2 bits per second. But by using BPSK, I will be able to transmit only 1 bit per second. So that is first thing. So to understand that, let us have a look. How do we convey the information in case of QPSK, right? So as I already said, QPSK means what? It is quadrature phase shift keying, right? Quadrature phase shift keying. So means there will be 4 phases, right? In case of binary phase shift keying, only 2 phases. Bi means 2, right? Only I will be conveying symbol 0 with one phase and symbol 1 with another phase. In case of quadrature phase shift keying, so I can have 4 phases. Those 4 phases are what? Pi by 4, 3 pi by 4, 5 pi by 4, and 7 pi by 4. So this is one possibility. Another thing, another possible phases, what I can say, 0, 90, 180, 270, again back to 360 degree I can say, right? Is also a phase difference of 90 degree, right? So let us try to understand this first. So for this given set of phases, right, pi by 4, 3 pi by 4, 5 pi by 4, and 7 pi by 4. So 4 phases are there. So with respect to that, I said means each die bit, what I can say, means 2 bits, right? Die bits, I can transmit with one phase. Okay. So with respect to that, I am saying 2 bits will be transmitted per second. Fine. I will show some more diagrams, then you will be able to get that clarity. So now let me say, how do I express this QPSK transmitted signal? Okay, so this is what the expression for saying the QPSK transmitted signal, that is SI of t is equal to what? Square root of 2e by t cosine of 2 pi fct plus 2i minus 1 of pi by 4. It is very simple expression. Don't get scared looking at this. What is this so big? It is nothing like that. So here E is the energy of the symbol. Okay, here 2 bits is equal to 1 symbol, what I can say. Okay, earlier I used to say E suffix B in case of BPSK, right? So that is energy per bit. Here energy per symbol. So here 2 bits is equal to 1 symbol. That is the one difference. The second in is here T, means T is a symbol duration. In the previous case, it was TB, that is bit duration. Okay, here 2 bits is equal to 1 symbol. So that is why I written here square root of 2e by t. Hope that point is clear. E is the transmitted signal energy per symbol. Okay, here symbol means 2 bits and t is the symbol duration. And cosine of 2 pi fct is there anyhow, first part. So second is about the phase, right? So why, how beautifully it is expressed mathematically, you just think. It is right. See, what is this? 2i minus 1 of pi by 4. If I substitute the value of I as 1, then what? 2 minus 1 is what? 1. Means I get a phase shift of pi by 4. Right? When I is equal to 2, means 2 into 2, that is 4. 4 minus 1 is 3. So 3 pi by 4 I get. Right? When I is equal to 2. Similarly, when I is equal to 3, so 6 minus 1, that is 7 pi by 4 I get. No, 3 into 2, 6, 6 minus 1 is 5, 5 pi by 4. When I is 4, that is 8 minus 1, that is 7, 7 pi by 4 I get. So, very beautifully it is written, the QPSK transmitted signal. Okay. So, SI of t is equal to square root of 2e by t cosine of 2 pi fct plus of what? 2i minus 1 of pi by 4. Right, where the value of I can vary from 1 to 4, okay, over the symbol interval 0 to t. So this is how we express the QPSK transmitted signal, right? Okay, so what is the carrier frequency? Already I said NC by T, where NC is a number of cycles, what I can choose. Then I said, no, here we use a pair of bits, that is, it is known as die bit. Okay, means here one example I have taken, that is 10000111. So it is a gray encoded bits. We have taken in this as what? Gray encoded set of die bits. So you all know what is gray code, right? There will be a single bit change, right? If I take a first bit as 10, then there will be a single bit change. It means next will become 00. Next it will be 01. Next it will be 11, like that, right? So I think with this I will stop today. Just have a look. Let me continue further discussion in the tomorrow. Yes, hope my PPT was there.